Well, the title of this work is Lithium Silicate Solid Electrolyte Prepared in situ on silicon electrodes in a Li-ion battery during charge discharge. My name is Nadia Oropesa Miranda, and this work have as a co-author the Dr. Enrique Quiroga González. We belong to Institute of Physics of Benemérita Universidad Autónoma de Puebla. Mm, it's well known solid electrolytes present superior characteristics than liquid electrolytes in Li-ion batteries, but with higher cost. The present work proposed the synthesis of a solid electrolyte based on electrochemical lithiated silicon oxide, starting from thermally ground silicon oxide films. In particular, this work will discuss aspects of the fast transformation of silicon oxide when it is lithiated and the possibility of ionic transport through it. In lithium-ion batteries, the electrolyte is one of the vital parts allowing ion exchange. In recent years, there is a trend towards the use of solid electrolytes, but they are expensive. A solid electrolyte option based on abundant elements are lithium silicates, which have ionic conductivity of 10 to the power of 6 to 10 to the power of 9 centimeter. They have a crystalline structure that allows transport of lithium ions. And the problem is that despite the fact the electrolyte is based on silicon, which is a very abundant material, it is still very expensive due to the way it is synthesized. Knowing that silicon oxide is naturally formed on silicon and that it can be electrochemically lithiated by discharging silicon electrodes. In this project, the synthesis of a solid electrolyte based on lithiated silicon oxide through an electrochemical route is proposed. It has been reported that during the lithiation of silicon electrodes that contain native oxide, mm, the silicates lithium were formed. This is indication that lithium silicates can be produced easily and at low cost. The idea of this thesis work is to test if these silicates can be used as a solid electrolyte in a lithium-ion batteries. Mm, the silicon oxide films were grown on electronic-grade silicon wafers by thermal oxidation under oxygen flow at 920 Celsius degrees. The thickness of the films were 20 nanometers and 5 nanometers. Additionally, a silicon sample with a previously specified layer of about 1 micrometer thickness using the metal-assisted chemical etching technique was also oxidized. Etching was performed in two steps. First depositing nanoparticles with a solution composed of a volume ratio of 25 to 5 of 1 molar aqueous solution of silver nitrate and hydrofluoric acid, and etching in an etching solution composed of a volume ratio of 4432 of deionized water, hydrogen peroxide, and hydrofluoric acid. The formed fourth layer was the transformed into oxide by thermal oxidation, with the idea that the porosity serves for mass transport of the liquid electrolyte. The different oxidized silicon samples were assembled as electrodes in battery half cells with lithium as counter-electrode and LP30 as liquid electrolyte. The cells were subsequently subject to charge-discharge cycle. From the curves of storage capacity against the number of cycles, a Coulombic efficiency of less than 20% was observed in the first cycle in all the samples. As example, figure 1 shows the case of the sample with 20 nanometers oxide. The low efficiency has been commonly attributed to the formation of solid electrolyte interface on silicon electrodes. However, in the present cases, and silicon oxide layer is also participating in the process. Figure 2 shows a typical voltammogram of silicon anodes to see at which potentials the formation of lithium silicon phases occurs. To elucidate whether there is an effect of this layer, curve of the derivative of the voltage with respect to the capacity, which are analogous to voltampograms, were calculated from the cycling data. As an example, figure 3 shows curves of the first and third cycle of the lithium period of the silicon electrode. For the sample with 20 nanometers is oxide. In cycle 1, there are peaks that disappear in cycle 3. One can be attributed to the say formation and other to the irreversible lithiation of silicon oxide. These peaks are also shown in 5 nanometer sample. Despite these irreversible reactions, silicon continues to be lithiated, indicating that lithiated silicon oxide allows ion transport. Mm, we can conclude silicon oxide can be irreversible lithiated but allows ionic transport. The silicon electrode used as anode in lithium-ion batteries, representing a step forward to creation of a solid electrolyte. And thank you.